Every skyscraper has blueprints. Every blockbuster, well, it has a director. And, every single successful tech innovation, think about the apps on your phone or the big networks powering universities like Tarleton, has something just as vital: IT project management. Seriously, without that structure, that rigorous planning, the world's most ambitious digital ideas, they just collapse before they even get close to delivering value. Welcome back to the Deep Dive. Today we're tackling something absolutely critical. We're focusing squarely on the constraint that, let's be honest, probably causes the most stress and conflict in projects' time. We are talking about project schedule management. It's like the strategic architecture you need to turn abstract scope into actual timely delivery. In this deep dive, it's essential if you want to understand how to manage all those related phases of a complex IT project.
That's exactly right. And look, for serious professionals, and I'm talking especially to you graduate students listening in from the Dr. Sam Pack College of Business at Tarleton State University, working through BCIS 5 through 51, mastering these schedule principles isn't optional. It's non-negotiable. This is really where the theory you learn, it becomes real, actionable leadership skill. It lets you move past just knowing definitions and start truly evaluating situations, applying these concepts strategically. That's hitting KO2 right there.
Yeah, our goal today is basically to hand you the strategic roadmap. How do you plan, lead, and crucially deliver IT projects on time? We'll start small, defining the work, then structure it into a timeline, find that critical path, and wrap up by showing how you use advanced metrics to actually control performance.
And we really want this to be immediately useful for you. So if you find this deep dive valuable, if it helps connect those dots between, say, the textbook and the real-world control room, please do us a favor. Like it, follow, share it, maybe leave a comment. Oh, and definitely check the episode description. We'll put links to resources there that expand on everything we talk about today. It's crucial stuff. Okay, let's kick things off right at the beginning. Why is schedule management? Why does it cause so much conflict? I mean, more than scope or cost, often. Well, think about it. Unlike scope, which can sometimes flex, or cost, where you might find more budget, time is finite. It ticks away. Plus, it's constantly interacting with resource availability, which is usually also finite. So the goal isn't just hitting some arbitrary date. It's developing and then sticking to a realistic schedule, one that cuts waste and really maximizes efficiency.
Okay, a realistic schedule. And to build that, there's a formal process, right? A sequence of steps. Can you walk us through those? There are 6, I believe.
That's right. 6 key processes, mostly in the planning phase. First, you lay the groundwork. Plan schedule management. That gives you your schedule management plan, the rule book, essentially. Then you get into the details. Define activities, sequence activities, estimate activity durations, develop schedule, and then finally, when you're executing, you control the schedule.
Okay, I want to pause on that second one, define activities. Now, in our previous deep dives, we talked a lot about the work breakdown structure, the WBS, from scope management. Doesn't the WBS already define all the work? Why do we need this separate step? It feels a bit redundant, maybe.
That's a really good question. And it gets right to the core logic of how project management frameworks like the PMBOK guide are structured. You're right, the WBS, which comes out of scope management, is all about decomposition, breaking down the deliverables. What are we building? It gives you those work packages. But for scheduling, you need something smaller, more actionable than a work package usually is. An activity, or sometimes we just call it a task, is that smaller piece. It's the bit of work that you can assign a specific duration to, allocate costs for, and assign resources to.
Gotcha. So the WBS might say build user authentication module. That's the deliverable, the work package. But the define activity step breaks that down into things like design database schema for users, code login API endpoint, write unit tests for login, perform security scan. Each of those can be timed and scheduled individually.
Exactly. The WBS is the blueprint overview. Activity definition puts the really granular step-by-step execution details onto that blueprint. And you simply can't sequence things properly or estimate durations accurately until you have that level of detail. It really highlights that strong link between scope the WBS and time the activities. Demonstrates that knowledge of terms. KO3.
Okay, makes sense. So once we have those activities defined, the next big hurdle is estimating how long they'll take. Duration estimation. Yeah. And this is notoriously tricky, right? Especially in IT where things change fast. How do we even think about duration? Is it just the time someone spends working on it?
That's a critical distinction you're hitting on. We need to separate effort from duration. Effort is the actual work time, the number of person hours or person days needed to do the task, fingers on the keyboard coding, or time spent in a design meeting. Duration, on the other hand, is the total elapsed calendar time. That includes the effort plus any waiting time, review time, lag time. Think about paint drying, concrete curing, or waiting for approvals. So maybe writing a complex database migration script takes 8 hours of pure effort, but the duration might be, say, 48 hours because you need a 24-hour observation window after running it, and then 16 business hours for management sign-off. Huge difference.
Right. That difference is key. So how do we estimate that duration? What are the techniques? Maybe start with the quickest one.
Okay. The quickest, but usually the least accurate, is analogous estimating. Some people call it top-down estimating. You basically look at similar projects or activities you've done in the past. You say, okay, last year we did a small data warehousing migration, kind of like this one, and it took 10 weeks. So you estimate this current one will also take 10 weeks, maybe adjusting a bit for perceived complexity. It's fast, it's cheap, relies heavily on expert judgment or sometimes just gut feeling. Best used really early on when you don't have much detail. Gives you a ballpark figure, a rough order of magnitude.
Okay, fast and broad. What if the work is more standardized, something we do often? Is there a more precise way then?
Absolutely. That's where parametric estimating shines. This is super useful for repetitive tasks. Think about things like provisioning standard virtual machines, deploying routine security patches, installing workstations. It works by taking a known productivity rate, the time it takes to complete one unit of work, and multiplying it by the total quantity of work. For instance, if your historical data shows your team can configure and deploy, say, 5 standard servers per day, and the project requires deploying 50 servers, well, 50 divided by 5 is 10. Your estimate is 10 days. It uses those measurable historical rates, so it's usually much more accurate than just an analogous guess.
Nice. Okay, quick but rough with analogous, more precise for repetitive work with parametric. What's the gold standard if we need maximum accuracy?
That would be bottom-up estimating. This is where you go down to the lowest level of detail in your WBS, those individual activities we just defined. You estimate the duration for each of those highly specific granular tasks. Then you aggregate them. You sum up the durations of all the tasks within a work package to get the work package duration. Then sum up the work packages and so on, all the way up the WBS hierarchy. Now, this method gives you the most accurate, most detailed estimate, often called a definitive estimate. But it's also the most time-consuming and costly way to estimate. It requires that you've really defined the work in detail and usually needs input from the people who will actually be doing the work.
Right, a trade-off between accuracy and the effort it takes to get the estimate. Okay, now let's tackle the really tricky stuff. What about tasks where there's just a ton of uncertainty? R&D, cutting-edge tech development, where you don't have good historical data or standardized units.
Yeah, that's the norm in a lot of IT, isn't it? For those high uncertainty situations, we move to 3-point estimating. Instead of asking someone for a single number, a single guess for duration, you ask for 3. An optimistic O estimate. What if everything goes perfectly? Best case scenario, no delays, resources are ideal. A pessimistic P estimate. What if everything that can go wrong does go wrong? Murphy's Law hits hard. Major roadblocks, risks materialize. And crucially, a most likely M estimate. What's the realistic duration based on experience and normal conditions?
Okay, O, M, and P. Optimistic, most likely, pessimistic. But we don't just average those 3, do we? This is where PERT comes in, right? The program evaluation or review technique.
Exactly. PERT takes those 3 points and uses a weighted average. It's not just O plus M plus P3. It applies a specific formula based on statistical probability, specifically an approximation of the beta distribution. It has a fascinating history, actually, developed for the Navy's Polaris missile program back in the 50s.
Okay, let's state that formula clearly, because this is a key takeaway, especially for the graduate students listening. How is the PERT expected time calculated?
Right. The formula for the PERT expected time, TE, is optimistic plus 4 times most likely plus pessimistic, 6. So TE equals O plus 4M plus P, 6 6s.
The key there is multiplying the most likely M estimate by 4. Why? Why give it so much more weight than the optimistic or pessimistic estimates?
That weighting comes directly from probability theory and the shape of the beta distribution curve, which is often used to model task durations. Statistically speaking, the most likely outcome is, by definition, the one expected to occur most often. It's the peak of the probability curve. By weighting M 4 times more heavily, the PERT formula pulls the final estimate towards that realistic central value. It acknowledges the possibility of the extremes, O and P, but prevents them from skewing the estimate too much, especially if one of them is a wild outlier. It gives you a statistically more reliable figure than a simple average.
Let's use that driving commute analogy from the outline to make it concrete.
Okay, yeah, good idea. Let's say your commute. Optimistic, O equal 30 minutes. No traffic, all green lights. Most likely M equals 60 minutes, normal conditions. Pessimistic P equals 120 minutes, major accident, terrible weather. A simple average is 30 plus 60 plus 120, 3 equals 70 minutes. But the PERT calculation is 30 plus 4, 60 plus 1, 6. That's 30 plus 240 plus 120, 6 with 396 equals 65 minutes. See how it pulls the estimate slightly lower than the simple average, closer to the most likely? It smooths out the impact of that really bad day.
That's a great illustration. It moves estimating from just guessing to using a statistically validated figure. But wait, there's more to PERT than just getting a better average, isn't there? Something about risk.
Ah, yes. This is where PERT gets really powerful for project managers. It doesn't just give you the expected duration, it also allows you to quantify the uncertainty or risk associated with that estimate. You can calculate the standard deviation for each activity's duration estimate. The formula for standard deviation in PERT is approximately optimistic times 6. So in our commute example, sigma 120/36 equals 96 equals 15 minutes.
Okay, so we have a standard deviation for each task. What does that tell us? Why is that useful?
Well, standard deviation measures the spread or dispersion of the possible durations. A larger standard deviation means more uncertainty, more risk for that specific task. But the real magic happens when you look at the whole project. You can calculate the standard deviation for all activities on the critical path. We'll define that path in a moment. By summing the variance is just standard deviation squared, figma 22, of all critical path activities, you get the total project variance. Then take the square root of that total variance and you have the overall project standard deviation.
Wow, okay, so you get a single number representing the uncertainty of the entire project's finish date.
Precisely. And with that project standard deviation, you can start making probabilistic statements about the completion date. You can say things like, based on our PERT analysis, there's a 68% probability we'll finish between date X and date Y, which is the expected date plus not one standard deviation, and a 95% probability we'll finish between day A and date B, expected date plus NAIC 2 standard deviations. This transforms risk management. It moves it from qualitative guesswork, yeah, this feels risky, to quantitative probability. You can actually evaluate the likelihood of hitting deadlines, which is a direct application of KO3 and SO2 managing phases and understanding terms and techniques.
That's fantastic. Turning estimation into a core risk management tool. Okay, really powerful stuff. All right, so we've defined the activities, we've estimated their durations using techniques like TERT. Now we need to put them in order, right? Sequence them and visualize the whole plan. Let's start with the most common visual tool people probably associate with project schedules.
That would almost certainly be the Gantt chart. Everyone's seen them. Simple bar chart format. You list the activities down the side, usually vertically, and then time is shown horizontally. Each activity gets a bar showing its start date, finish date, and duration. They're really good for communicating schedule information, especially milestones and overall progress, to a wide audience, including stakeholders who aren't deep in the project details. And crucially, during the project, you often use a tracking Gantt chart. This shows the original plan bars, the baseline, right alongside new bars representing the actual progress. So you can immediately see if you're ahead, behind, or on track for each task. Fundamental for control.
Gantt charts are great for seeing when, but maybe not always why. They don't always clearly show the dependencies, the logical links between tasks, especially in complex projects.
That's their main limitation. For visualizing the logical flow and the dependencies, we need network diagrams. These diagrams really map out the sequence of work. Now, there are a couple of ways to draw them. The older method is the arrow diagramming method, ADM, also called activity on arrow, AOA. Here, the arrows themselves represent the activities, and the nodes, circles, represent start 10 points. It can get a bit cumbersome with dummy activities needed sometimes. Most modern project management software, especially things like Microsoft Project, which many IT departments use, relies on the precedence diagramming method, PDM. In PDM, the nodes, usually boxes, represent the activities, and the arrows simply show the relationships or dependencies between them. It's generally considered more flexible and easier to understand.
Okay, PDM it is. So to build that PDM network diagram, we need to understand the dependencies, those arrows connecting the boxes. These define the sequence. What types are there?
We usually categorize dependencies in a couple of ways. First, by their nature. Mandatory dependencies, sometimes called hard logic. These are inherent in the nature of the work itself. You simply cannot do B until A is done. You have to write the code before you can test the code. You have to build the server hardware before you can install the operating system. Then you have discretionary dependencies, or soft logic. These are defined by the project team based on best practices, preferences, or sometimes just convenience. Maybe you could start integration testing before all unit tests are done, but the team decides, as a best practice, to wait. Project managers need to be careful with discretionary dependencies because you're deliberately restricting scheduling flexibility. You should always document why you chose that sequence. And we also always need to consider external dependencies. These involve relationships between project activities and things outside the project's control. Waiting for a hardware vendor to deliver servers, waiting for a legal or regulatory approval, waiting for another project team to finish their part, these can be major schedule risks.
Mandatory, discretionary, external. Got it. Now, within those, PDM defines specific relationship types between two tasks, right? The 4 types.
Yes, PDM defines 4 logical relationships. Let's use some IT examples to make them clear. 1, finish to start, FS. This is the most common, probably 90% of dependencies. Activity A must finish before activity B can start. Example, the network infrastructure setup A must finish before you can start deploying the application servers onto that network B. 2, start to start, SS. Activity A must start before activity B can start. They might run in parallel for a while, but B can't kick off until A has begun. Example, writing the user documentation, A must start before the user training sessions. B can start. You need some draft material to begin training, even if the final docs aren't ready. 3, finish to finish, FF. Activity A must finish before activity B can finish. They might run in parallel, but B can't wrap up until A is done. Example, system testing A must finish before the final user acceptance testing sign-off B can finish. You need confirmation the system works before users give the final OK. 4, start to finish, SF. This one is the least common and sometimes confuses people. Activity A must start before activity B can finish. Example, the new 24/7 monitoring system, A, must start running before the old, less reliable monitoring system. B can be fully decommissioned and turned off. You can't finish shutting down the old one until the new one has started providing coverage.
That SF example with the monitoring system makes it click. Okay, so once we've mapped out all the activities and linked them with these FS, SS, FF, SF dependencies in our network diagram, what's the big payoff? What does this allow us to calculate?
The big payoff is identifying the critical path using the critical path method, CPM. The critical path is defined as the sequence of activities that determines the longest overall duration for the project. It's the path through that network diagram that takes the most time from start to finish. And here's the crucial strategic insight. The length of the critical path dictates the earliest possible completion date for the entire project. Any delay, even 1 hour on any activity that lies on that critical path, will directly delay the project's final completion date unless you can recover the time later.
The longest path determines the shortest project duration. A bit counterintuitive, but makes sense. And the defining characteristic of activities on the critical path is that they have the least amount of, what's the term? Float, slack.
Exactly. Float or slack, the terms are generally used interchangeably. Float is the amount of time that a specific activity can be delayed from its early start date without delaying the overall project completion date or violating a schedule constraint. Think of float as scheduling flexibility. It's the wiggle room you have. Activities on the critical path, by definition, have 0 float. Any delay hits the project deadline immediately. Tasks not on the critical path will have some positive amount of float.
Okay, 0 float on the critical path, positive float elsewhere. Is all float created equal, though? I think there are different types.
That's a sharp point. For real strategic control, you need to understand the difference between total float and free float. Total float, or total slack, is the amount of time an activity can be delayed without delaying the project completion date. Here's the catch. Total float often belongs to an entire path of activities, not just one task. If the first activity in a path with 10 days of total float uses up all 10 days, then all the subsequent activities on that path now have 0 float. They become critical. So using total float needs careful coordination. Free float, or free slack, is the amount of time an activity can be delayed without delaying the early start date of its immediate successor activity. This is a really useful tactical float for a PM. If a task has 3 days of free float, the team doing that task can delay by up to 3 days without impacting any other task or the project deadline. It's a localized buffer. Strategically, you might assign tasks with more free float to less experienced team members, giving them a bit of a safety net without jeopardizing the overall schedule.
That difference is huge. Total float is shared, affects the deadline eventually. Free float is local, doesn't impact successors immediately. Great distinction. Okay, but sometimes, even after we find the critical path, the resulting project duration is just too long. The business needs it sooner. What can we do then? We need to compress the schedule.
Right. When the calculated schedule doesn't meet the required deadlines, we look at schedule compression techniques. There are two main ones. The first is crashing. Crashing involves analyzing cost and schedule trade-offs to gain the maximum schedule compression for the least additional cost. Typically, this means adding more resources to specific activities on the critical path. Examples include paying for overtime, bringing in extra personnel, or maybe using more expensive but faster technology or tools. You focus the extra cost on the critical path activities where shortening the duration will actually shorten the project.
Makes sense. Throw money or resources at the problem, specifically on the critical path. What's the other technique?
The other is fast tracking. Fast tracking involves taking activities that were originally planned to be done in sequence, a finish to start dependency, and changing the logic to do them partially or fully in parallel, maybe a start to start dependency. For example, maybe you plan to fully complete the database design before starting any coding. Fast tracking might mean you start coding the initial modules based on a partially approved design while the design team finishes the rest. The big downside. Fast tracking almost always increases project risk. You're starting downstream work before the upstream work is finalized, which can lead to rework, integration problems, or quality issues if things change.
So crashing costs more money, fast tracking adds more risk. Important trade-offs for a PM to evaluate KO2. Now, all these techniques, CPM, PEP, crashing, fast tracking, they sound very logical, very mechanical, but projects involve people. And people aren't always perfectly logical, are they?
Yeah.
Now let's talk about the human element, the people issues and estimation bias.
Ah, yes. This is often where the beautifully calculated schedule meets messy reality. And it's where leadership skills become just as important as technical skills. We run into a few common human behavioral patterns that sabotage schedules. One is the famous Parkinson's Law. Attributed to Cyril Northcote Parkinson, it basically states that work expands so as to fill the time available for its completion. If you give a team member 3 weeks to do a task they secretly know they could probably do in 1 week, well, chances are it will take the full 3 weeks. There's little incentive to finish early.
Right. And the related issue is fairly common maybe in academic settings, but definitely in the workplace too.
You're probably thinking of the student syndrome. It's essentially procrastination. People tend to wait until the last possible moment before they start working seriously on a task. Even if they have float, they often wait until their float is gone and then start putting pressure on the deadline.
Parkinson's Law and student syndrome. Okay.
Yeah.
And these behaviors, maybe combined with a fear of being blamed if something goes wrong, often lead to.
They lead directly to the very damaging practice of padding estimates. This is where team members or even functional managers intentionally inflate their duration estimates. They add hidden safety time or buffers into their estimates for individual tasks beyond what a realistic PERT calculation would suggest.
Padding. I mean, on the surface, it sounds kind of prudent, right? Building in a safety net. Why is padding considered unprofessional and actually dangerous in serious project management?
It's dangerous for several critical reasons. First, it completely undermines the integrity and transparency of the schedule baseline. If the schedule is full of hidden padding, the project manager loses visibility into where the real risks are. A genuinely difficult, high-risk task might look safe on paper because it's padded, while a simple task might look long. The PM can't manage risks they can't see. Second, padding often leads to inefficient resource use. People might finish tasks early relative to the padded estimate, but not report it, leading to wasted time and increased overall project cost. Parkinson's Law kicks in. And third, and perhaps most damaging to team morale and trust, padding erodes credibility. If tasks consistently finish way earlier than estimated, it makes the estimators look either incompetent or dishonest. It damages the trust between the project manager and the team, which is essential for open communication about real problems. Professionalism demands realistic estimates, with risks managed explicitly through things like contingency reserves or buffers, not hidden padding. Okay, so we've established the critical path method, CPM, is really powerful for managing schedule based on task dependencies. But, as we hinted, it often makes a big assumption that you have the resources you need when you need them. In the real world, especially in IT, projects are almost always constrained by resources. You only have one lead security architect or 2 senior database admins or limited access to that expensive testing environment. This reality, the resource bottleneck, led to the development of a different approach, critical chain project management, or CCPM.
Right, critical chain. Developed by Eliyahu Goldratt based on his theory of constraints. So if CPM is task-centric, CCPM is fundamentally resource-centric. How does that change the game?
Exactly. The core idea of theory of constraints, TOC, is that any system's output is limited by its constraint, its bottleneck. In CCPM, we apply that to project schedules. We start by identifying the critical path based on task dependencies, just like in CPM, but then we overlay the resource constraints. We look at where activities require the same limited resource. The path that is longest, considering both task dependencies and resource dependencies, becomes the critical chain. It might be different from the original critical path.
Okay, so the critical chain factors in resource scarcity, and you mentioned CCPM discourages padding individual task estimates. It pushes for more aggressive, maybe 50-50 probability estimates for each task. If we take out that hidden padding, how does CCPM protect the project schedule from delays? Because delays will happen.
That's where the buffer system in CCPM comes in, and it's fundamentally different from the concept of float in CPM. Instead of individual tasks having hidden or calculated float, CCPM uses explicit, strategically placed buffers of time that are not assigned to specific tasks. These buffers are managed by the project manager, not the team members doing the tasks. There are two main types. First, a single, large project buffer is placed at the very end of the entire critical chain. Its job is solely to protect the project's final completion date from variations along the chain. Second, feeding buffers are placed at points where non-critical chains of tasks merge into the critical chain. These feeding buffers protect the critical chain from delays occurring on those non-critical paths. Essentially, you squeeze the padding out of individual tasks and consolidate that safety time into visible, managed buffers.
So the buffers absorb the uncertainty rather than hiding it in each task. That sounds much more transparent. What about the behavioral side? How does CCPM handle things like multitasking?
That's another huge difference. CPM kind of implicitly allows, or at least doesn't prevent, multitasking. People work on several things at once. CCPM actively discourages multitasking, especially for resources working on the critical chain. The philosophy is that task switching, or context switching, introduces significant delays and inefficiencies. In a CCPM environment, team members are encouraged, even pushed, to focus 100% on their current critical chain task until it's complete, then immediately pull the next task. The goal is to keep the work flowing through the constraint, the critical chain, as quickly as possible. It requires a different mindset.
Focus, single tasking on the constraint, explicit buffers. Quite a different approach. Okay, let's shift back to more general resource management within potentially a CPM framework. What if we just have situations where people are scheduled for too much work in a given week? How do PMs handle that?
When you have resources assigned more work than they can realistically do in a period, say, someone scheduled for 60 hours in a 40-hour week, that's overallocation. You need resource optimization techniques. The first main technique is resource leveling. Leveling aims to fix overallocations by adjusting the schedule. You apply resource constraints, like no one works more than 45 hours a week. To meet these constraints, you might have to delay the start date of certain tasks, even tasks on the critical path. So the crucial outcome of resource leveling is that it can, and often does, change the critical path and result in a later project completion date. You're prioritizing resource limits over the original schedule.
Can you give a quick example of leveling in action?
Sure. Imagine your top cybersecurity analyst is assigned to critical tasks A, B, and C this week, totaling 60 hours of work. Task C is on the critical path. Your company policy is a 40-hour week. To level this resource, you might have to push the start of Task C into next week. Because Task C is critical, pushing it back directly delays the entire project. That's resource leveling. You accepted a schedule delay to fix the overallocation.
Got it. Delaying the project to respect resource limits. What's the alternative technique?
The alternative is resource smoothing. Smoothing also adjusts activities and resource assignments, but its goal is to achieve a more uniform, consistent level of resource usage over time, maybe preventing huge peaks and troughs in someone's workload. The key difference is that resource smoothing only uses the existing float, total float or free float, available on non-critical activities. It does not change the project's critical path, and therefore it does not delay the project completion date. It's about making the workload more manageable within the existing schedule flexibility.
How would smoothing look different in practice using maybe that QA analyst example?
Okay. Let's say your lead QA analyst is scheduled for 30 hours of testing work in week 1, then only 10 hours in week 2, then 20 hours in week 3. But maybe the entire test phase has 5 days of total float. Resource smoothing might look at this and say, let's use some of that float. It could shift some of week 1's work into week 2, aiming for a more even load, like 20 hours each week for all 3 weeks. The total work and the final deadline remain the same, but the analyst's workload is more balanced, potentially improving focus and reducing burnout, without impacting the critical path. It's optimization within the existing constraints.
Leveling changes the end date. Smoothing doesn't. Crucial difference. Okay, one last area in strategic scheduling. What about projects where the uncertainty isn't just in duration or resources, but the scope itself is likely to change? High-tech R&D, new product development. How do you schedule when you don't even know exactly what you'll be building later on?
That's where traditional, detailed upfront planning breaks down. For those situations, we often use rolling wave planning. It's an iterative planning technique, very common in agile environments, but also used in predictive projects with high uncertainty. The idea is you plan the work that's happening soon, the next wave, maybe the next few weeks, or the next phase in great detail. You define activities, estimate durations, assign resources meticulously for that near-term work. But the work that's further out in the future, you plan that only at a much higher level. Maybe just defining major deliverables or work packages without breaking them down into detailed activities yet. Then, as the project progresses and you get closer to that future work, you progressively elaborate on it, planning the next wave in detail. It allows the plan and even the scope to evolve as you learn more. Great for managing projects with changing requirements, SO2.
Rolling wave planning. Progressive elaboration. Makes sense for uncertainty. And what about quantifying the combined impact of all these uncertainties, duration, cost, maybe even scope risks on the overall project outcome? Is there a way to simulate that?
Yes. The most common technique for that kind of integrated risk analysis is Monte Carlo analysis or Monte Carlo simulation. It's a powerful what-if simulation technique. It leverages those three-point estimates, optimistic, most likely, pessimistic we discussed for PERT, but it applies them to all uncertain variables, potentially task durations, costs, resource availability, etc. You need specialized software for this. The software essentially runs the entire project schedule simulation thousands, maybe tens of thousands of times. In each simulation run, it randomly picks a value for each uncertain activity's duration or cost based on its three-point estimate and probability distribution like beta or triangular.
Thousands of simulated project runs.
Yeah.
What does that produce? What's the output?
The output is a probability distribution for the project's completion date and/or total cost, often visualized as an S-curve. This curve tells you the likelihood of achieving different outcomes. For example, it might show there's only a 30% chance of finishing by the original target date, but an 85% chance of finishing within 2 weeks after that date. Or it might show the probability of exceeding the budget by a certain amount. It gives decision makers a much richer probabilistic view of the project's potential outcomes, considering the combined impact of many individual risks. It's probably the most sophisticated form of quantitative schedule and cost risk analysis available, SO2.
Okay, so we've done a ton of planning. We've defined work, estimated time using PERT, maybe used CPM or CCPM to find the critical path chain, optimized resources, even simulated risks with Monte Carlo. Now, the project is underway. We're executing. We need to track how we're actually doing compared to that plan. But before we can measure performance, we need the yardstick, right? The thing we measure against.
Absolutely. That yardstick is the schedule baseline. It's the formally approved version of the project schedule. It's documented, agreed upon by stakeholders, and it's the standard against which all future progress will be measured. It's crucial to remember that the schedule baseline is just one part of the overall performance measurement baseline, PMB. The PMB integrates three baselines: the schedule baseline, the scope baseline, which is the approved WBS and its dictionary, and the cost baseline, the time-phased budget. These three together define the plan.
Integrated and approved, which means you don't just change it lightly, right? If things slip a bit, you don't just redraw the baseline.
Exactly right. The baseline represents the commitment. Any changes to the schedule baseline or the scope or cost baselines should only happen through a formal, documented change control process. If scope is added or a major unavoidable delay occurs, you might formally rebaseline, but it's a significant event. Having that stable baseline is absolutely critical for control. Without it, you have no objective reference point. You can't really say if you're ahead or behind schedule or over or under budget if the target keeps moving unofficially.
Okay, stable baseline established. Now, how do we measure progress against it? This brings us to arguably the gold standard for integrated project control, earned value management, EVM. You called it the not-so-secret weapon before. Why is it so powerful?
EVM is powerful because it integrates scope, schedule, and cost into a single framework to measure project performance and progress objectively. It's not just about tracking costs spent or tracking time passed. It asks a more sophisticated question. It asks, based on the work we plan to do, the time that has passed, and the money we've spent, what is the value of the work we have actually completed? To answer that, EVM relies on three fundamental data points. Mastering these is key. KO3.
All right, let's define those three core EVM concepts clearly.
Okay. The three pillars of EVM are 1. Planned value, PV. This is technically the budgeted cost of work scheduled, BCWS. Think of it as how much value did we plan to have earned by this point in time according to the schedule baseline. It represents the budgeted cost of the work scheduled to be done up to the status date. 2. Actual cost, AC. This is the actual cost of work performed, ACWP. This one's usually straightforward. How much money have we actually spent to accomplish the work done so far? It's the real cost incurred. 3. Earned value, EV. This is the budgeted cost of work performed, BCWP. This is the linchpin, the clever part. It represents the value of the work actually completed to date, measured in terms of the budget originally allocated for that specific work. How much of the planned budget have we actually earned based on the progress we've made?
PV, AC, EV.
Planned value.
Actual cost, earned value. Okay, theory is one thing. Let's make this really concrete. We need an example. Let's imagine a relatively simple IT project, maybe upgrading a department's servers. Let's say it's planned to take 50 days and has a total budget of $50,000. And we're checking the status exactly halfway through, at day 25.
Perfect scenario. Okay, at day 25, according to our approved schedule baseline, we should be 50% complete with the project work. So our planned value, PV, is 50% of the total budget. 50% of $50,000 is $25,000. By today, day 25, we plan to have accomplished work worth $25,000. That's our PV.
Okay, PV 25K. Now let's look at the reality. Let's say the finance department reports that for all the work done on this project up to day 25, the total charges are $28,000. Maybe we needed some unexpected emergency support or hardware costs were higher. So our actual cost, AT, is $28,000.
AC equals 28K. Got it. Now for the crucial one, earned value, EV. The project manager needs to assess how much work has actually been completed. Forget the schedule for a moment, forget the cost. Just look at the physical progress against the WBS. Let's say the PM assesses that, despite being halfway through the calendar time, the team has only genuinely completed 40% of the total project scope. Maybe some early tasks took longer than expected. To get EV, we take that percentage of work actually completed, 40%, and multiply it by the total project budget, $50,000. So EV, 40% of $50,000, $20,000. We've owned $20,000 worth of the planned budget based on the work actually finished.
Okay, fantastic. So recap, status date, well, equals day 25, halfway. Total budget, $50, PV, 25K, what we plan to have done. AC, 28K, what we actually spent. EV, 20K, the value of the work actually done. Now we have the raw data. How do we use it to analyze performance? We need the variances, right? Cost variance and schedule variance.
Exactly. The variances tell us if we're off plan and by how much in dollar terms. Cost variance, CV. The formula is CV equals EVAC. In our example, CV equals $20,000, $28,000 equals $8,000.
Okay.
Interpretation. A negative CV means we spent more than the value we've earned. So we're only $8,000 over budget. Not good.
Okay, CV equals $8 over budget. What about the schedule? How does EVM measure schedule performance?
Schedule variance, SV. The formula is SV equals EVPV. In our example, SV $20,000, $25,000, and equal $5,000. Interpretation. A negative SV means we've earned less value than we plan to have earned by this date. So we are currently behind schedule. We're $5,000 worth of work behind where the plan said we should be.
Over budget by $8, behind schedule by $5 worth of work. That's already illuminating. But variances in dollars, what about efficiency? That's where the indexes come in, CPI and SPI.
Precisely. The performance indexes give us ratios, which are often more powerful for comparing performance across projects or over time. They tell us about our efficiency. Cost Performance Index, CPI. The formula is CPI equals EVAC. In our example, CPI less than $1, $28,000, approximately 0.71. Interpretation. A CPI less than 1 means we're getting less value out than the money we're putting in. A CPI of 0.71 means for every actual dollar we spent, we only earned about 71 cents worth of planned value. That's poor cost efficiency.
Only getting 71 cents on the dollar. Ouch. Okay, and schedule efficiency.
Schedule Performance Index, SPI. The formula is SPI EVPV. In our example, SPI equals $20,000, $25,000, 0.80. Interpretation. An SPI less than 1 means we're progressing slower than planned. An SPI of 0.80 means we're only progressing at 80% of the rate originally planned. We're working slower than scheduled.
CPI 0.71, SPI 0.80, both below 1.0, which is the target. So this project is clearly in trouble. Over budget, behind schedule, and inefficient on both fronts. Just calculating those three numbers, PD, AC, EV, and then these simple formulas give such a clear, objective picture. That's the real power, isn't it?
It absolutely is. EVM provides the foundation for data-driven decision-making, that's SO2, using skills for managing phases. When a PM can report a CPI of 0.71 and an SPI of 0.80, the conversation with stakeholders becomes much more focused and objective than just saying, we're running a bit late and over budget. Furthermore, these indexes are crucial for accurate forecasting. There are formulas that use CPI and SPI to calculate the estimate at completion, EAC, predicting the total final cost and the estimate to complete ETC for schedule predicting how much longer it will take. This gives the PM proactive control, allowing them to identify problems early and take corrective action. It's a cornerstone of effective project control and evaluating situations, KO2. So we've spent a lot of time on these powerful tools and techniques, PERT, CPM, CCPM, EVM, but it's really important to remember that how we use these tools, or even if we use all of them, depends heavily on the overall project management methodology or approach we choose. The methodology is like the overarching strategy. It dictates how we handle planning, execution, and especially how we manage time and adapt to change.
Good point. Let's briefly revisit the most traditional approach, the one that probably relies most heavily on detailed upfront scheduling like we've been discussing. That's predictive project management, right? Often called waterfall.
Exactly. Predictive, or waterfall, models work best when the requirements are well understood and stable up front. Think linear, sequential phases. You finish requirements, then design, then build, then test, then deploy. Schedule management here is rigorous. You create that detailed WBS, define activities, build a network diagram, find the critical path, establish the baseline, and then you track progress meticulously against that baseline using EVM. It's excellent for projects where predictability, stability, safety, and compliance are paramount. Think large construction projects, maybe some government system implementations, or projects with very long timelines where change is expected to be minimal or very controlled. The main limitation, though, especially in fast-moving fields like IT, is its inflexibility. If significant changes do arise after you've started executing, incorporating them can be very difficult, costly, and disruptive to that carefully crafted schedule.
Right, the inflexibility challenge, which of course led to the rise of Agile or adaptive methodologies. How does scheduling work differently there? It seems almost opposite in philosophy.
It is radically different in many ways. Agile approaches like Scrum or Kanban were born out of the need to handle high uncertainty, rapidly changing requirements, and the need for faster feedback cycles. Agile emphasizes flexibility, customer collaboration, and delivering working software in short, fixed-duration cycles, typically called sprints or iterations, maybe lasting 1 to 4 widths. So, schedule management changes focus dramatically. Instead of trying to perfectly predict and control a long-term end date months or years out, Agile focuses intensely on time boxing. The schedule constraint becomes the fixed length of the sprint. The team commits to delivering a certain amount of prioritized work within that sprint. The schedule management is about maximizing the value delivered in that short time box and then replanning for the next sprint based on feedback and changing priorities. Overall, project completion time is often seen as an outcome rather than a fixed constraint up front. It's about continuous value delivery and adaptation.
So less focus on the big, upfront critical path, more focus on delivering value within short, regular time boxes. But what about the real world? Many IT projects aren't purely predictable or purely chaotic. You might have technical uncertainty that screams agile, but also fixed budgets or hard regulatory deadlines that demand some predictability. What happens then?
That situation is incredibly common, and it's exactly why hybrid project management has become so prevalent, relevant to SO1 researching current topics. Most mature organizations now recognize that forcing a project into a purely predictive or purely agile box often doesn't work. A hybrid approach aims to blend the strengths of both. You select the best methodology for different phases or aspects of the project.
Can you give an example of what a common hybrid model looks like in practice for an IT project?
Sure. A very common pattern is Agile predictive integration, sometimes called a phased, agile, or Wardchild approach. You might use a predictive framework for the overall project structure. So you do upfront work to define the high-level scope, establish the overall budget, identify major milestones, especially external ones like regulatory deadlines or market launch windows, and maybe create a high-level schedule baseline. This satisfies the need for governance and long-term visibility for stakeholders. Then, for the actual development and delivery phases, the coding, testing, integration, you switch to an agile methodology like Scrum. The development team works in sprints, delivering features iteratively, getting rapid feedback, and adapting to technical challenges within those sprints. This way, you get the structured oversight and forecasting from the predictive wrapper, but the flexibility and responsiveness of Agile in the core execution.
That makes a lot of sense. You get the best of both worlds, potentially. Structure for the business, flexibility for the tech team. Seems like a good way to manage risk, too.
Definitely. The predictive planning helps identify and manage high-level strategic risks and provides a framework for stakeholder communication. The agile execution allows the team to rapidly identify and mitigate technical risks or respond to changing user needs discovered during development. Hybrid approaches are often essential for successfully navigating those complex IT projects that have both business constraints and technical uncertainties. Knowing how to blend these is a key skill for managing modern projects. KO2, SO2.
And underpinning all of this,
Yeah.
regardless of methodology, are the software tools, right?
Oh, absolutely. Technology support is indispensable today. SO3, using tools as part of a team project. Whether you're using something like Microsoft Project, which is very strong for traditional predictive scheduling, Gantt charts, critical path analysis, and resource leveling, or whether you're using tools like Jira, Azure DevOps boards, or similar platforms that are built around agile concepts like backlogs, sprints, Kanban boards, and burndown charts. The software helps automate calculations, visualize progress, and facilitate collaboration. But, and this is the crucial takeaway, the software is only as good as the understanding of the person using it. You can easily create a nonsensical schedule in Microsoft Project if you don't understand dependencies or the critical path. You can misuse an agile tool if you don't grasp the principles of iterative delivery or backlog prioritization. Mastering the underlying concepts we've talked about today, WBS, activity definition, PSE, CPM, EVM, the differences between methodologies, that's what allows you to use the software effectively and truly demonstrate your knowledge and skill. KO3. The tool doesn't replace the thinking. Hashtag tag outro.
Wow, okay. We have covered a lot of ground today in this deep dive into the architecture of time in IT projects. That constraint that really does make or break things. We started right down at the basics, defining those individual activities, then moved into estimating how long they'll take using techniques like analogous, parametric, and the statistical power of PERT. We mapped out the logical flow with network diagrams, found that all important critical path using CPM, maybe even consider the resource-focused critical chain with CCPM.
And critically, we didn't stop at planning. We saw how to gain real control during execution using the integrated metrics of earned value management, calculating those variances, CV and SV, and especially the performance indexes, CPI and SPI, that gives you that transparent, quantifiable measure of project health against your schedule baseline. It's how you know if you're really on track.
Absolutely. And mastering these techniques from being able to properly define an activity list all the way through calculating and interpreting your SPI, that's how you, as a current or future leader, especially those of you in BCIS 5351, transform ambiguity and uncertainty into successful, timely project delivery. You're learning the core project management terms, the techniques, the evaluation skills necessary to manage those complex, related phases of any significant IT endeavor, whether you're the project manager or an active contributing team member.
We really hope this deep dive has helped connect some of those dots for you between the theory and the practical application. We strongly encourage you to maybe dig a bit deeper into EVM calculations or PERT concepts using the resources in the description. And of course, if this was helpful, please do take a second to subscribe, follow, share it with colleagues or classmates, and perhaps leave a comment with your thoughts or questions. We appreciate the feedback.
Okay, before we sign off, here's a final reflective question for you to mull over, tying back to the importance of what we discussed. If every single IT project worldwide suddenly failed tomorrow morning, what part of your daily life, your work, your access to information or services from online ordering to banking to healthcare records to communication, what would come crashing down first? And what does that potential chaos tell you about the often invisible but utterly foundational importance of things like the schedule baseline in keeping our modern world running?
That is a sobering thought, really highlights the stakes. Well, thank you for joining us today for this exploration.
Behind every successful app launch you use, every seamless online order you place, every bit of digital innovation that shapes our lives, there's IT project management working diligently, often behind the scenes, making it possible. Until next time, keep exploring the world where ideas become projects and projects shape our future.